Hello students, we are back again with the next topic of Fourier transform, and that is properties of Fourier transform. And in properties of Fourier transform, we have four properties and we will go on seeing one by one. Alright, so the first property is addition or linearity theorem. So what we mean by addition or linearity theorem? So we are just going on adding the Fourier transform of every function of t, right? So the theorem states that if f of t is equals to a1 f1 of t plus a2 f2 of t and so on, then the Fourier transform of f of t is equal to a1 f1 of omega plus a2 f2 of omega plus and so on, where f1 of omega, f2 of omega are the Fourier transforms of f1 of t, f2 of t and so on. And a1, a2 etc. they are constants. Alright. So now let us prove this. So to prove we have to start with the LHS, or before that we have to start with the definition of Fourier transform. So what is the definition of Fourier transform? Fourier transform f of omega is equals to 1 by root 2 pi minus infinity to plus infinity f of t e raised to minus I omega dt. So this is the definition of Fourier transform of a function f of t. But according to our theorem, what is f of t equal to? F of t is a1 f1 of t plus a2 f2 of t and so on. So let's substitute that. So we have 1 by root 2 pi, okay, minus infinity to plus infinity a1 f1 of t plus a2 f2 of t plus so on. This is our f of t, and what is left here? E raised to minus I omega t dt. Right? Now what is our next step? Our next step is to remove the bracket. So to remove the bracket, we will go on multiplying 1 by root 2 pi and e raised to minus I omega t inside the bracket. So what we get here? We get 1 by root 2 pi integration minus infinity to plus infinity a1 f1 of t into e raised to minus I omega t dt. So this is, I am going to write it as a1 f1 of t e raised to minus I omega t dt plus, what is our next term? 1 by root 2 pi, again we are going to multiply inside. So we have 1 by root 2 pi integration minus infinity to plus infinity a2 f2 of t into e raised to minus I omega t dt. Right? So this is going to continue and so on. So plus so on. Now, since a1 is a constant, a2 is a constant, the constants come out of the integral sign. So I can write this as a1 by root 2 pi, or I can just write it as a1 into 1 by root 2 pi integration minus infinity to infinity f1 of t into e raised to minus I omega t dt plus, here I have a2 into 1 by root 2 pi integration minus infinity to infinity f2 of t e raised to minus I omega t dt plus so on. Now, if we see the definition of Fourier transform, we see that it is this particular definition and this particular part of our proof is similar, right? That is 1 by root 2 pi f of t e raised to minus I omega t. Here we have 1 by root 2 pi integration f1 of t e raised to minus I omega t dt. So this I will substitute to be, a1 is going to remain the same. This part is nothing but the Fourier transform of f1 of t. So what is the Fourier transform of f1 of t? It is f1 of omega. So I will write it as a1 f1 of omega. plus similarly a2. What is this? This is Fourier transform of f2 of t, which is nothing but f2 of omega. So I have here it as a2 f2 of omega plus and so on. So what is this? This is nothing but our RHS. So this is equal to RHS, thus proved. What did we prove now? When I add the functions of t, I get the Fourier transform of function of t also to be equal to the sum of the Fourier transforms of various functions of t. That is, we are adding or we are showing the linearity in the Fourier transform. Okay, so this is our first theorem. Let's move on to the second theorem. Now the second theorem is similarity or change of scale property. Okay, so the theorem states that, or the property states that, if f of omega is a Fourier transform of f of t, then Fourier transform of f of at is equal to 1 by a f of omega by a. So again we start the proof by defining the Fourier transform. So what is the definition? F of omega is equal to 1 by root 2 pi integration minus infinity to plus infinity f of t e raised to minus I omega t dt. Right? Now instead of f of t, what do we have? We have f of at. So I'll write this as f of omega is equal to, or the Fourier transform of f of at, I can write Fourier transform of f of at is equal to 1 by root 2 pi integration minus infinity to plus infinity f of at e raised to minus I omega t dt. Alright. Now what I'll do is, I will substitute y is equals to 80. Okay. So let y is equals to 80. So this means t is equals to what? Y by a. And what about dt? Because if I have to remove this t function and put it as y function, I have to convert everything into y. So y is equals to 80. So if I differentiate this, I have dy is equals to, a is a constant, so a into dt, right? Or I can say dt is equals to dy by a. So all this we will substitute in this particular expression. So what is this now? Fourier transform of f of at is equal to 1 by root 2 pi integration minus infinity to plus infinity f of y e raised to minus I omega. What is t? Y by a. So it is y by a into dt. Dt is dy by a. Right? Now I will try to simplify this expression and write next. So this is equal to 1 by root 2 pi into 1 by a. See this 1 by a, I am taking it outside the integral sign. Right? So 1 by a, I am taking it outside the integral sign. What else is left inside? Minus infinity to plus infinity f of y. Okay. Now what I'll write here? E raised to minus I omega by a into y. I'll write it like this. Okay. Into dy. Right. Now when I compare this definition with this is in the form of t and this is in the form of y. And where I have only omega, I have omega by a, and where I have t, I have y. Right? And 1 by root 2 pi is also there. Integration minus infinity to plus infinity is also there. Instead of f of t, I have f of y. instead of e raised to minus I omega t, I have e raised to minus I omega by a into y. And dt, instead of dt, I have dy. Now I can write the same thing as this is equal to 1 by a f of omega by a. Now since it was only omega, we had omega here. Now I have omega by a, so I'll write it as omega by a. And 1 by a is a constant which is outside, so I'm writing it as 1 by a. So what is this now? This is a RHS, and thus it is proved. What we have proved here? We have proved that Fourier transform of f of at is equal to 1 by a f of omega by a. So this is what we proved, and this is the change of scale property or the similarity property. So both are same, but we are changing the scale. Okay, instead of saying f of omega, we are saying f of omega by a, right? Instead of writing it in the form of t, we are writing it in the form of y. That's it. Okay, so let's move on to the third property. The third property is called as the shifting property. So we are shifting something here. What we are going to shift, that we'll see now, right? So the property states that if f of omega is the Fourier transform of f of t, then f of t plus or minus a is equal to e raised to plus or minus of I omega a into f of omega. So what is being shifted? So let's see that. So if a function is shifted in the positive or the negative direction by an amount a, that is t plus or minus a, then no Fourier component changes its amplitude, but it changes its phase. Phase, P-H-A-S-E, phase. So it is going to suffer a phase change. It is not changing its amplitude, but it is changing its phase. That is e raised to plus or minus I omega a. Right? So let's prove that. Again we start by the definition. So what is our definition? Fourier transform of f of t is equals to f of omega, which is equal to 1 by 2 pi minus infinity to plus infinity f of t e raised to minus I omega t dt. So this is our definition. So what is our next step? We have to substitute, instead of f of t, we have to substitute as f of t plus or minus a. This is our LHS. So let's substitute that. So we have 1 by root 2 pi minus infinity to plus infinity f of t plus or minus a, okay, e raised to minus I omega t dt. So here we are again repeating the same procedure what we did in the earlier part. That is, we are substituting t plus or minus a equal to y, right? So we have let t plus or minus a is equals to y. So what is t? What is t? T is equals to y minus or plus of a. So plus becomes minus, minus becomes plus, right? And what is dt? dt is equals to dy, because a is a constant, right? So a becomes, differentiation of a becomes equal to 0. So we have dt is equals to dy, right? So now what we have to do? We have to go on substituting. So what we have here? We have equal to 1 by root 2 pi minus infinity to plus infinity f of y. T plus or minus a is equals to y. So we have f of y. And here we have e raised to minus I omega. Instead of t, we have to write it as y minus or plus of a, right, into dy. Right? Now what I can do here is, I can split it up. So I have minus infinity to plus infinity f of y e raised to minus I omega y into, okay, e raised to, minus of minus becomes plus, okay. So we have I omega a plus or minus. So minus of minus becomes plus, minus of plus becomes minus. So plus or minus I omega a into dy. Now since a is a constant, so this whole part becomes a constant because we have nothing with respect to y here. So this part I can take it outside. So I have, this is equal to e raised to plus or minus I omega a into 1 by root 2 pi integration minus infinity to plus infinity f of y e raised to minus I omega y into dy. Right? So now this is similar to our definition f of omega. So I can write this as, this is equal to e raised to plus or minus I omega a f of omega, because we have omega only here. So we're going to write it as f of omega, which is equal to RHS, and thus it is proved. What we proved? We proved that the Fourier transform of f of t plus or minus a is equal to, the Fourier transform of f of t plus or minus a is equals to e raised to plus or minus I omega a into f of omega. So the next property, the fourth property, is the modulation property. So we will prove that now. The fourth property or the modulation property states that the Fourier sine transform of f of t sine at, this is equal to half of Fourier cosine transform of omega minus a minus Fourier cosine of omega plus a. Right? So we are going to define the sine transform and the cosine transform first. So the sine transform is Fourier sine transform of f of t. I can write it as fs of omega. So this is equal to f of t sine omega t dt. Okay. And Fourier cosine transform of f of t, this is equal to 0 to infinity f of t cos omega t dt, which I can write it as fc of omega. Okay. Now, the question is, the Fourier sine transform of f of t sine at. Apart from f of t, I have an extra term, that is sine at. So in this, if I add an extra term sine at, what is going to happen? So fs of f of t sine at, this is equal to 0 to infinity f of t sine omega t into sine at, into sine at dt. Right? So now, if I see this expression, I can see that this is nothing but sine A into sine B. Now what is sine A into sine B? Sine A into sine B is equal to cos of A plus B by 2 minus cos of A minus B by 2. Or I can write this as half of cos of A plus B minus cos of A minus B. I have taken half common out. Now this I am going to substitute in my above equation, that is here. So we get here fs of f of t sine at is equal to 1 by 2 0 to infinity. I am taking this 1 by 2 outside the integral sign. So what else I have here? I have f of t. I am going to keep it like that. And here instead of a I have omega t, and instead of b I have at. So I will write this as cos of omega plus a into t minus cos of omega minus a into t dt. Since we have t common out, see omega t and et, we have t common out, so I am going to write it as omega plus a into t, omega minus a into t. Okay. Now we will separate these two as two different integrals. So we are going to write it as half of 0 to infinity f of t. Okay. This I am going to write it as one integral and this is the other integral. So it is going to be cos of omega plus a into t dt minus half of 0 to infinity f of t cos of omega minus a into t dt. Right? So now if I compare it with this definition of Fourier cosine transform, I see that they both are similar except for this omega. So I have omega minus a, so this becomes fc of omega minus a. Here I have omega plus a, so it becomes fc of omega plus a. So I will write this as half of, I'll take the half common out. So what we have? Fc of omega plus a minus Fc of omega minus a. So this is nothing but our RHS. So thus proved that the Fourier sine transform of f of t sin a t is equal to half of Fc of omega plus a minus Fc of omega minus a. So these are the four properties of Fourier transform. So students, if you have any doubt, please comment in the comment box so that we can solve in our coming videos. And please don't forget to subscribe and share it to your friends so that they will also get benefited. Thank you. Hope you have a good day.